Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guest today is William Hurley, called Whirly, the CEO of Strangeworks. Strangeworks, according to the notes, it launched earlier this year during a South by Southwest keynote, and the company has raised $4 million in a seed round. They formed some partnerships, as they say, with IBM, CERN, and Stack Overflow, and they're going to be offering a subscription service that allows developers to run quantum experiences on a number of simulators and emulators. And it sounds like they've got a quantum computer or two, stuck in their pocket that people can use. So it looks like a Amazon Web Services for quantum computing at first blush. But I'm going to ask more about it. So, William, how are you doing?
I'm doing great. Thanks for having me on today.
Yeah. So I'm never as good at explaining things as the CEOs or founders. So tell me, let's step back again. Talk to me about Strangeworks. Where did the concept come from, and what's the premise of the company?
So personally, I'd been looking into quantum computing for about 5 years before we started the company and making some minor investments for about 3. I'm fascinated with the technology. And I had sold my last company to Goldman Sachs. I was looking at, doing the startup thing again. That's kind of my forte. And I really wanted to get into quantum computing. And I did a bunch of research and saw that, this is something that's been talked about for decades. And it was seeming to me like the timing was starting to get right. I mean, if you look at the history, you had the fifth Savoy Conference in 1927 with Heisenberg and, Einstein and Schrodinger, where the quantum mechanics thing kind of came into being. And then, in 82, you had Benioff and Feynman kind of come up with the idea of using the spin of a particle, as a bit, if you will. And then there was kind of nothing. I mean, Los Alamos had 7 qubits in 2000. In 2006, the Quantum Institute and MIT had 12. And from 2006 to, pretty much recently, there wasn't anything. And it looked like quantum computing was just going to stay on the same trajectory. Well, in 2017, you had Microsoft introduce Q#, which is a big gamble if they don't think that quantum computing is close. You had IBM and Intel both have 17 qubits. Then at the end of the year, IBM had 50. Then at the beginning of this year, 2018, Google had 72. And then just recently, Rigetti announced their path to 128. So I look at that, and I looked at the patents, I looked at the investment. There were, a handful, 5 or 6 quantum computing startups as of a couple of years ago. Today, there's 75 plus worldwide. And so I just feel like this is a field that has the momentum and it's happening. It's something, like I said, I've been fascinated with for years. And, it's a much bigger risk than other options I could have taken. But I was like, I want to do something in this space. And when I looked at it, I saw that there was a bunch of stuff lacking in the areas of development tools and management tools for enterprise. Most of these companies are founded by people from academia, which is fantastic. I'd like to see a lot more university, knowledge transfer and startups created. I've always been a big advocate of that. And you basically get into a situation where, all right, this is really really interesting.
All right, well, let me ask you a few questions about it. Quantum computing, I've done a number of interviews on it. I still find it difficult to understand. So let's start with qubits. I can, because I've used computers, I can understand, all right, this processor is 2.5 gigahertz, et cetera. A lot of people kind of have a feel for it. Well, how about qubits? What can you give me as a good feel for what's the potential of 1 qubit versus 100? So when I hear that this company has a 17 qubit computer, it doesn't sound impressive to me, but maybe I should be impressed. So give me a sense of the scale of what a qubit is.
This is funny because this is part of what we're trying to do as a company with the tools and in our efforts with doing standards with like the IEEE and stuff, because this is where it gets confusing. So let me give you a quick example. You have 2 bits and you add 2 bits, right? You have 4 bits, you have, 16 outcomes. But if I have 2 qubits and I add a qubit, in theory, I have 2 to the n, the number of bits, right? So it exponentially grows faster in the computational power primarily in the areas of optimization and combinatorial type problems, right? But here's the thing. What is a qubit? Because you have quantum annealers, you have physical and logical qubits, you have circuit gate models, you have topological qubits, you have bits that are done with ion trapping, et cetera, et cetera. And so there's not like, whereas we have in silicon, here's what a bit is, here's how a transistor works, it's at this many nanometers and fab this way and everything. You don't really have that on the quantum side. We're at a moment in time, which I think is one of the most exciting times to be alive in computing, because what is happening will change computing more in the next 10 years than computing has changed in the last 100. But we don't have any standards, points of references. So you ask a question like, well, give me an idea of the power. It's like, well, that power is different on an annealer than it is on a circuit gate model, than it would be on a theoretical topological. And also there could be all these different ways. And the reason that is because there is an Achilles heel to quantum computing right now. And that's fidelity of these systems. So adding a qubit isn't necessarily hard, but adding a qubit and keeping the noise level where the system has a higher fidelity is hard, right? Microsoft is trying to address this with topology. IBM and Google and Rigetti are all doing their own kind of error correction and noise reductions that they're trying to do. Companies like Control Q, our friends down in Australia, they're only focused on basically software that helps with the error correction and the noise handling. So remember, the fidelity of that system is super important to the accuracy of the answer, just as much as the number of qubits. So that's something I think we need to discuss more openly, which is, how are we defining qubits? How are we, kind of making sure everybody can understand this and understand what that actually means to the computations they're trying to do. And that's part of why we led the formation of the IEEE's Quantum Computing Standards Work Group, and we're chairing it, is because we're doing a standard on nomenclature, so people can just have a reference to be like, oh, a qubit, there's like 12 different possible types, and these three are kind of what people are working on. But it's also, more importantly, why we put forward a standard on performance benchmarking, because we all know that for every claim from D-Wave that they're super fast, there's a Scott Aronson paper, right, that says, yeah, actually, I did this on the plane on my laptop and it's faster because you didn't make a solver. Or Helmut Katzgraber or Andrew Ochoa, who now works for us, do these things that show that actually traditional computing, works. And, we forget the basics of how this technology will be adopted. Yes, we've got VC investment. Okay. Yes, governments are investing. But here's the problem. To make it an industry, we need companies to invest. And for companies to invest, it will not matter if quantum computing is 100,000 times as fast if it costs 1 million times as much. It'll never make it into the enterprise, right? So there's all of these other factors that are driving these papers, driving these conversations. And at Strangeworks, we're focused on a much more, in our opinion, and it is our opinion, a much more pragmatic, much more practical approach to, this is where quantum computing is today. This is where it'll be in 3 years. This is where we think it'll be in 10 years. And what does that actually mean you can use it for? Because while 128 qubits is a huge jump from having 17 last year, it's still not really enough to do anything earth-shattering with, right? I mean, eventually you're going to have...
Let's step through that. So it sounds like, there's a lot of hype around quantum computing. You're still excited about it, obviously, so you see it as great potential. So, for a layperson that does not know anything beyond like these buzzwords and things being thrown about, what's the state of it right now? What do you think it'll be in the next few years? And then beyond that, probably, who knows? Let's focus on that.
Yeah. So I think right now where we're at is we're in a good position for companies that want to adopt quantum computing to start playing around with it. So there's a dozen companies, Strangeworks, what we offer you is a way to do these quantum experiments. We show you a timeline of where we think it's advancing. Our software adds new technologies onto the platform as they become available. But more importantly, I think, where it's going in the next few years, I think we're about 24 to 36 months from it becoming actually useful. Now, that doesn't mean it's going to solve all of the world's problems, but you'll be able as an enterprise to run experiments and simulations of things that you will derive value from. You'll have enterprise outcomes, and you can calculate a return on investment, right? And that's how we look at it. So I think that's about 3 years out. And then where we go from there, I always hesitate to say, because here's the fact: noise reduction and fidelity of the system, those things, the error correction, just like when we had error correction in computers, think back and compare it. You're a layperson. That's awesome. It's We're trying to make sure every layperson understands it. We don't think this should be something, held in the realm of physicists, which is why we want to help every software developer get access, get tools where they can play with this technology because of two factors. Number one, I don't think such a small population of people will create all the amazing solutions. I think that if we get 2 or 3 million developers that are just software developers, data scientists, people of that nature working on problems with quantum computing, I think they're the ones that are going to come up with the super amazing uses for it, right? And the real value proposition. But past 3 years, my vision gets kind of blurry. And the reason is that there are so many companies now dedicated to error correction, so much effort dedicated to making the fidelity of these systems higher across the board, from Google and IBM and Rigetti to Control Q and even us and everybody. Someone will crack that. And when that happens, and you can add qubits and you can keep the fidelity of the system higher, I can't tell you that we won't go from what I think is 300 or so qubits in the next 24 to 36 months to 100,000 qubits or 1 million qubits. And by the way, the reason I can't tell you that is because there may be new physics problems in the quantum realm that we discover only when we get to 100,000 qubits or maybe 50,000, right? And so think of it like compared to your phone. We all have a phone in our pocket. Apple just announced the new iPhone. Okay, that new iPhone is the first chip that has a 7 nanometer scale. So what that means is that chip has about 3 billion transistors on it. So think back in your computer history to when you had to be an electrical engineer to program a computer, and think about how widespread computers were used. You had to understand the voltage between the physical gates. Then a few years later, many years later, you only had to understand that there were gates. And today we turn out developers from all these coding schools who probably don't even know that there's gates, right? And so look at all of the world's benefits that we've seen from computing as we widen the pool of people that had access to it. Well, right now, to use a quantum computer, you have to be a physicist, right? We're trying to help take that at Strangeworks to where you just have to understand some basic physics, right? And then hopefully eventually to where the physics are all abstracted and you don't have to understand any of that. You just have to understand how to write code, because we believe these things shouldn't be viewed as a new, you're not going to have a 10,000 quantum computer data center, not for a long time. So think of them like a GPU or a TPU, right? Like a TensorFlow processing unit or graphics co-processing unit. Think of them as a coprocessor or a cloud processor. Now it becomes really interesting. And by the way, that's one reason Rigetti, who's one of our many partners, has a pretty interesting approach, because they're building a hybrid architecture that's both classical and quantum. And the reason is they can work the delays down to almost nothing by having your classical software and algorithms run, send it what it needs to a quantum coprocessor that it's essentially very tightly integrated with and back, right? So there's a lot of cool, approaches in this space. We look at them as a coprocessor.
Yeah, quick question. I don't know. You talked a lot about errors involved in computation. So where are the sources of error? Why are qubits, I guess for lack of a better word, messy? Why are there computational errors, and how do you fix it?
Well, I wish I knew how to fix it and have the solution. That would be amazing. But when you look at quantum error correction, right, the problem is that there's decoherence in the system and there's quantum noise, okay? Classical error correction uses redundancy, right? So the simplest way to store information multiple times, and if these copies are later found to disagree, you take a majority vote, you say, okay, this is what we think it is. You can't copy quantum information, right? There's this thing called the no cloning theorem, right? And so it presents an obstacle to basically formulating a theory around quantum error correction. Now, it's possible to spread the information of one qubit into some entangled state over several. Shor's algorithm, creator Peter Shor first discovered a method for doing that. And there's a bunch of other stuff you can do, but it's a really complicated problem. Decoherence, okay, is super, super important to understand in these systems. that is, when you look at a D wave, you see those pictures online of this big black box. There's not a lot in that box. That box's primary function is to shield from all of the particles hitting us from space and noise and environmental variables for these machines. They're kept using cryogenics, very cold, et cetera, et cetera. That's because when you look at a quantum computer like IBM's, it's a fraction of a second that it's really available, say on the 50 qubit machine, because, well, when you start calculating, the decoherence starts setting in. There's all these different um, environmental variables that are expressing this, affecting this. And so when you want to think about quantum error correction, and you can't copy the information, and you've got all of this, then in theory, a quantum error correcting code would protect the information against the errors, but it'd be in a really limited form, right? So this is a super complicated problem. It again has to do with not just the error correction, but with the decoherence and then of course the fidelity of these systems. And so it's super complicated, especially because we're not in the electrical based realm that we have been in, where we have a amazing amount of knowledge, right? I mean, electricity is still the power source for everything from your car to your phone to everything. And because of that, you're talking about now moving that into the quantum realm. And let's face it, when you talk quantum computing and you talk quantum mechanics, it goes back to what Feynman said, right? He said, if you think you know quantum mechanics, then, you probably don't, right? I'm paraphrasing, but that's basically what he said, because it's a very complicated domain, and a lot of that domain is still theoretical. Even things you read about that have been quote unquote proven have been proven in experiments, but there's could be a very long distance between those experiments and it actually being something that you can put into use. So the quantum error correction is just it's the thing that keeps me up at night, because if we don't solve it, then in the next few years, then I entered the market too early. And if we do solve it, then my timing was just perfect as a startup. But without solving for the error correction, without getting the fidelity higher and dealing with the decoherence, right? This kind of unavoidable noise that arises from these microscopic oscillations of these atoms, then, we're going to be kind of stuck in a rut for a little while. Think when you make a phone call on a congested network, right, or scratching a CD or whatever, it still works, but that's only because those systems have error correction, right?
The quantum systems you're saying right now they're very expensive because of the cooling required, because of the shielding required. They're also, I guess, for lack of a better word, buggy. They have tons of errors right now because we haven't been able to institute error correction. But they're super exciting and they show tons of promise. But these are, I guess, two of the fundamental problems right now with the field, right?
Yeah, they're the problems that I'm focused on, right? They're the problems that I'm focused on because they're what I think is the thing holding quantum computing back the most.
Okay, so what if we could delve a little bit into the science of error correction a little bit, and into the cooling? Why does a quantum computer, for instance, need to be cooled to such a low level? Why does that make it work? What's the answer to that?
Well, think about it like this. You're taking something, okay, an atom, right? It's in a constant state of vibration and motion, okay, and you're taking that and you're trying to use it effectively, like a bead on an abacus, right? So you need to basically keep that cold, because the colder you make it, the less motion those particles will have, right? They'll have the spin, but you can actually work with them and try to manipulate them in that state. And that's why you have, all of these patents, all of this work around cryogenics, that you're essentially cooling those to get it more stable as a system, right?
Okay.
MIT's, right. I think, runs, negative millikelvins. IBM's right around absolute zero. But these things vibrate, they rotate, they strongly interact with each other. And so, typically in the world, atoms have to really meet each other, be on top of each other before they see there's another one. So now, you're taking these and spreading them out in a system, trying to get them to work together, cooling them down to around 300 nanokelvins, just a few tenths of a millionth of a degree above absolute zero. And then you're trying to use that cooling to stop the movement and control them, right?
So just based on that, how would we scale quantum computers? Or, how would you ever have a portable device that's a quantum computer? Or do you think that's just never going to happen?
Well, so you may not have. So, okay, again, that goes out pretty far. But there's a bunch of opportunities to have something. So there's a thing called a linear optical quantum computer, right? So it's basically uses photons as information carriers, right? And uses linear optical elements, so beam splitters, phase shifters, things like that, to process the quantum information. And then uses photon detectors and what are called quantum memories to detect where the information is stored, detect it and store it. So there are, in a perfect sci-fi fantasy world, would I have the power of quantum computing in my pocket? Yes. But I don't believe that means you have a quantum computer in your laptop, nor do I believe that means you have it in your phone. Your phone, as a consumer, will take advantage of quantum computing, in my opinion, in the next 36 months. Because Google will have the quantum computers. They'll use things like Grover's algorithm to do search, and you will be the beneficiary of that speed. Because if you think of this classic phone book example, if you think of a classic phone book example, you search for a number. I have your number. I don't have your name. I'm searching through it line by line by line on a computer. A quantum computer, in theory, would need the root value of that to get to the same answer, right? So basically, it will improve things like search. It will improve things like autocorrect, which God knows we all need. So I think you'll have quantum computers doing work that will give you an improvement as a consumer over your phone, but your phone's not going to be using any quantum mechanics technology. Not unless we, have aliens land and give us the secrets of the universe or some major crazy advancement, because that would be extremely awesome, but also calculatedly complicated.
Okay, so it'll be more of a you will have a quantum computer in the cloud, but you'll at least have access to it, and it can do computation for you and make your computation better and faster, et cetera.
Yeah, exactly, right? And that's why we say there'll be things that large companies use to improve services they have that are existing, things like search, et cetera, et cetera. And there'll be things that you will take and run. Take Shor's algorithm. It has 5 steps. Only one of them do you really need a quantum computer for. So you would basically run step 1, 2, 3. Is it an even odd or odd number? Is it the factor of 2 coprimes? Pick a random number. Is that a factor? And when you got to step 4, which is kind of the, non-deterministic quantum magic, you would pop that up into the cloud, let the quantum computer process it, or if you're using a Rigetti system, it would pop over to the quantum functionality, and then it would come back, and you'd run step 5, which is to go through and check everything and be like, okay, we think we've got an answer, right? And that answer would be dependent upon the number of qubits and the fidelity of those qubits greatly. But that's how we see people using these, as far as the early adopters and enterprise go.
Okay. Again, what kind of specific computations would a quantum computer help with? Either of those cloud-based, and which ones, regular computers are just fine to do? Where's the special benefit of using quantum computing? What kind of problems or what kind of computation?
Well, there's a number, right? So problems that are optimization problems, right? So the classic traveling salesperson problem, things where you're trying to do optimization of traffic patterns, air traffic, deliveries, things like that. Those will probably be the things that it's most useful for the earliest, right? Things in chemistry, right? Which of course could help with everything from drug discovery and new drugs to, new materials and advances in material science. I think those will also be kind of some of the early problems that you'll see this be useful for. And then beyond that, you've got things in energy and finance and aerospace, quantum Monte Carlos, or things that will, help companies with their financial projections, things involving financial systems. I think you'll kind of see that. So I see the early adopters being in kind of like pharma and aerospace, and then companies that have optimization problems, whatever they may be. And I see even some of that in energy, and then of course expanding into energy, and then moving into finance and things of that nature as the technology evolves.
So what is Strangeworks going to have? It sounds like it's going to probably be a cloud-based model. Like you said, you'll let developers run simulations and have access to quantum computing. So do you guys have a quantum computer that you're going to be spinning up for people to use, or are you going to rely on another company and just provide the access and the pipelines to it? What's the model?
So we partner with IBM and Rigetti and others, and we use those systems, right? Because one of the things we think people need to be aware of is I don't think as an enterprise you can make a bet on a specific architecture or type of quantum computer, right? And even within one type of quantum computing, say circuit gates, Google and IBM and Rigetti have very different approaches. So we wanted you to be able to run the same calculation on all of those computers and start gathering the data for finding out, oh, you know what, Google is better at chemistry or IBM's better at finance, whatever the case may be, so that you can align your algorithm you're trying to run onto the best possible platform. That includes integrating it with your system and management and cost and all of that. So we're not building a quantum computer. Now, we have built our own simulator, and we've built other, housed other simulators so you can run everything very fast. But, that's kind of one of many offerings. I mean, we are very, 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 very focused on building community first and foremost. It is our belief that we're going to need, as many people involved in this as possible. I mean, think about it simply, like we can't be the best if there's no competition, right? And we're certainly not going to make all the advances in the space. You need people focused on the same thing as us and on different aspects and on the hardware and the software and middleware and all of this stuff. So to that extent, you mentioned our partnership with Stack Overflow earlier. We created quantumcomputing.stackexchange.com as a way of bringing more people in. So if you go to some of these quantum conferences, the two I went to last year, that doesn't mean there aren't ones where there's more people. There are about 100, 125 people at each of them, right? And those are two pretty well-known events. We now have over 3,500 people in the Stack Overflow community. And more importantly, we have a 94% answer rate. So that means out of 100 questions, 94 of them get an answer that is deemed correct by a community of 3,500 people, including some of the top minds at Google and IBM. I mean, the community's grown so much, IBM actually now links to it, and there's now quiz questions in there. Microsoft is starting to put Q-sharp questions in there. So, community and standards are kind of our focus for the first year. Yes, we have our platform built. Yes, it's in testing at a few customers. And yes, next year in Q1, we'll kind of release it to everybody, and we'll have a community edition that's free for everyone. Because again, we want to see people using this. But most importantly, we want to see there be a community first and some standards first, so that when you're a software developer and you write Python and you do some data science, or maybe you work in AI and you're like, I want to mess with quantum. We can't just give you tools and blindly throw them into that. We need to have a community that we can reference, where you can get answers to questions, where you can ask questions maybe that haven't been asked before. We need to have some standards so that you can say, oh, here's how I can test the performance benchmarking on my problem on these things in a way that is objective and not driven by one, hardware manufacturer or one software developer. So, those two things have been a big part of our efforts this year. In addition, we're supporting the Senate Bill 3141 and trying to help get funding to universities to do more research and to get this out into the larger quantum community here in the States. The Congress side just passed, the Senate side hopefully will pass as well. And so, there's a lot of that work that needs to be done. And it's not that people aren't doing it. We just feel that it's not being pushed hard enough. And if I have to take the first year of the company and help build a foundation of a much larger community and much larger industry, to make sure that everything makes sense for my product and for others, that's something we've always done. A lot of us in the team came from the open source world. We're very collaborative. It's how we have these partnerships we have so early on. It's how we've driven that community. Again, it's 3,500 people. If we do our job right, by middle of next year, I'm anticipating we'll have about 10,000 somewhere between 10,000 and 13,000 people in that community. And that's going to be super powerful and useful to everyone, right? It's very objective. We don't even moderate the community. We partnered with Stack Overflow to use their moderation process so that there's a bunch of other people. James Wooten, for example, was at the university in Switzerland, just left to work for IBM. He's one of the moderators, right? He doesn't work for me, doesn't have anything to do. And we think that's part of the strength of what we're doing in that community. So the software will be, again, mainly focused on software developers, getting them onboarded into Quantum as quickly as possible, getting them tool sets and algorithms and things they can use to jumpstart their development so that instead of trying to be the hero of Quantum, we can provide the tools and the technologies on which 1 million people can go do amazing, heroic, visionary stuff with this technology.
Well, very good. So what's your specific roadmap for the next 6 months to a year with Strangeworks?
So we're focused on our Q1 release of the product. As far as what we're looking to in the future, right now, we've got people in aerospace, people in energy, and people in finance, and about to have a couple companies in pharma using the tools and giving us feedback. We're using that to drive what our roadmap looks like. We've got a roadmap, but you can't develop it in a vacuum, right? Anybody who doesn't have customers beating up and being critical of these products is developing in a vacuum, and we don't want to do that. So, we're getting some early revenues. We're getting early traction with some really big names. We'll be doing some press releases between now and the end of the year on that. And then we're focused on March. That's when I tentatively have it slated to kind of release this to the world. And then there'll be a whole bunch of other people that tell me how it sucks and beat up on it and everything. And we'll take all of that feedback and iteratively develop it because, we want that criticism. Like we welcome whether it's some physicists saying, oh, we think this is wrong, or software developers saying, I don't understand this is easy, or customers or companies. That's how we're going to build the best product for developers in quantum computing. And we want to be very open about that, very transparent about what we're doing development-wise. But, again, sign a few more customers between now and the end of the year, integrate all this feedback in the product, release a community edition. Again, March is the time frame I have in mind. And then, from there, see where it goes. I mean, there's literally, in my opinion, hundreds of thousands, about millions of things you could build for this community. So we're certainly not short of options. And, we want the community to help drive both through Stack Overflow, through the product, through even our partnerships and even our competitors. I mean, we're super friendly with a lot of our competitors. We want to drive together things that will get the adoption for everyone across the board.
That's great. Yeah, building a community is the way to go because it's such a tough, pervasive problem, but it's going to bring so many benefits. So that's great.
Absolutely.
All right. So what's the best way for people to get in touch and to find out more and to join the community? I think it's probably number one, and collaborate. So
we would suggest people join the community. You just go to quantumcomputing.stackexchange.com. And you can sign up easily. We definitely, if you're a company that's a member of the IEEE or wants to be a member and work on the standards, you can just Google IEEE Quantum Computing Standards. It'll bring the pages right up, and you can contact me that way through Hurley, WHURLEY, at IEEE.org. And if you want to learn about Strangeworks, email me directly. I mean, we're a very flat organization, and there's no kind of weird hierarchy or interaction with our customers. Most of us have talked to every single one of them multiple times. I talk to all of them all the time. It's just WHURLEY at Strangeworks.com, and I'll be happy to talk to you myself.
That's great. Well, William, thanks for coming on the podcast. I appreciate it.
Hey, thanks for having me.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.